Okay, so we're looking at chapter 9 of your Memler's textbook today. So we kind of, like I said, we skipped forward yesterday up to chapters 7 and 8. Now we're doing chapter 9. So we're going to look at two major systems today. That is going to be your nervous system and your endocrine system. So we're going to talk about the two systems that control your body, right? The nervous system does it, in a pretty point A to point B, simple to understand version where it's just like, hey, I want to have something happen, and so your nervous system goes zap and makes it happen. But we're also going to talk a little bit about the endocrine system, which is also a control system. It's under the control of your nervous system, but it's how your nervous system sort of communicates in a different way with the body. And so it might cause like a certain gland to excrete something, and then that's running through your body. And the endocrine system is really cool because a lot of its effects are really powerful. But one of the problems with the endocrine system that we often feel is where, you create some type of hormone and it's running through your body. And hormones are really intense, but they're also kind of slow to respond. And so like maybe you'll make some adrenaline and then it stays in your body for a little while and you just stay kind of amped up and you're like, I should have calmed down by now, So it'll be kind of fun to talk a little bit about that. Now, our realm of like what we talk about in the endocrine system is relatively limited. Most of the time it's spent talking about, stress hormones and insulin and things like that, anabolic, catabolic hormones. But we'll go ahead and do a brief overview of kind of a big section of them. But before we kind of dive into our lesson here, let's go ahead and start it off with an interesting video so we can see what all this anatomy looks like, and we can shove those images into our head and understand what I mean when I say certain nerves. So crash course nervous system. All right, so here's our whoop, that's not right. Oh, it's a 2-minute ad. I got confused for a second. I was like, this video should be longer. All right, here we go.
Good morning. This morning was a typical morning for me. I woke up thinking about that dream that I keep having about the guy in the sloth suit, and then I got dressed because I was cold, and then I made some toast with butter because I was hungry, and then I let the dog out because she was whining and staring at me, and then I made some tea, but I let it cool off before I drank it because it burned my mouth yesterday. In addition to being just part of my morning ritual, all of these actions are examples of what my nervous system does for me. The weirdo dream, the sensation of cold air and hot tea, deciding what to put on the toast, going to the door, the sound of the dog, all that was processed and executed by electrical and chemical signals to and from nerve cells. You can't oversell the importance of the nervous system. It controls all the things, all your organs, all your physiological and psychological reactions, even your body's other major controlling force, the endocrine system, bows down before the nervous system. There is no you without it. There's no me without it. There's no dogs without it. There's no animals. There's no things. There's things. It's important. That's why we're dedicating the next several episodes to the fundamentals of the nervous system, its anatomy and organization, how it communicates, and what happens when it gets damaged. This is Mission Control, people. Even though pretty much all animals, except super simple ones like sponges, have a nervous system, ours is probably the most distinctive feature of our species. From writing novels to debating time travel to juggling knives, all of your thoughts and actions and emotions can be boiled down into three principal functions: sensory input, integration, and motor output. Imagine a spider walking onto your bare knee. The sensory receptors on your skin detect those 8 little legs. That information is your sensory input. From there, your nervous system processes that input and decides what should be done about it. That's called integration. Like, should I be all zen about it and just let it walk over me? Or should I not be zen and freak out and run around screaming, spider, your hand lashing out to remove the spider, and maybe your accompanying banshee scream is the motor output, the response that occurs when your nervous system activates certain parts of your body. As you can imagine, it takes a highly integrated system to detect, process, and act on data like this all the time. And when we talk about the nervous system, we're really talking about several levels of organization, starting with two main parts: the central and peripheral nervous systems. The central nervous system is your brain and spinal cord, the main control center. It's what decided to remove the spider and gave the order to your hand. Your peripheral nervous system is composed of all the nerves that branch off from the brain and spine that allow your central nervous system to communicate with the rest of your body. And since it's orientation, your peripheral system is set up to work in both directions. The sensory or afferent division is what picks up sensory stimuli, like, hey, there's an arachnid on you, and slings that information to the brain. Your motor or efferent division is the part that sends directions from your brain to the muscles and glands, like, hey, hand part, how about you do something about that spider? The motor division also includes the somatic or voluntary nervous system that rules your skeletal muscle movement, and the autonomic or involuntary nervous system that keeps your heart beating and your lungs breathing and your stomach churning. And finally, that autonomic system too has its own complementary forces. Its sympathetic division mobilizes the body into action and gets it all fired up like, ah, spider, while the parasympathetic division relaxes the body and talks it down like it wasn't a black widow or anything. You're fine, breathe. So that's the organization of your nervous system in a nutshell. But no matter what part you're talking about, they're all made up of mainly nervous tissue, which you'll remember is densely packed with cells. Maybe less than 20% of that tissue consists of extracellular space. Everything else, cells. The type of cells you most likely heard of are the neurons, or nerve cells, which respond to stimuli and transmit signals. These cells get all the publicity. They're the ones we're always thanking every time we ace an exam or think up a snappy comeback to an argument. But these wise guys really account for just a small part of your nervous tissue because they are surrounded and protected by gaggles of neuroglia, or glial cells. Once considered just the scaffolding or glue that held neurons together, we now know that our different glial cell types serve many other important functions, and they make up about half of the mass of your brain, outnumbering their neuron colleagues by about 10 to 1. Star-shaped astrocytes are found in your central nervous system and are your most abundant and versatile glial cells. They anchor neurons to their blood supply and govern the exchange of materials between neurons and capillaries. Also in your central nervous system are your protective microglial cells. They're smaller and kind of thorny looking and act as the main source of immune defense against invading microorganisms in the brain and spinal cord. Your ependymal cells line cavities in your brain and spinal cord and create, secrete, and circulate cerebrospinal fluid that fills those cavities and cushions those organs. And finally, your central nervous system's oligodendrocytes wrap around neurons, producing an insulating barrier called the myelin sheath. Now, over in your peripheral nervous system, there are just two kinds of glial cells. Satellite cells do mainly in the peripheral system what astrocyte cells do in the central system. They surround and support neuron cell bodies, while Schwann cells are similar to your oligodendrocytes in that they wrap around axons and make that insulating myelin sheath. So don't sell your glial cells short. They're in the majority cell-wise, but of course, when it comes to passing tests and winning arguments, most of the heavy lifting is done by the neurons. And they're not all the same. They're actually highly specialized, coming in all shapes and sizes, from tiny ones in your brain to the ones that run the entire length of your leg. But they do all share three super cool things in common. Number one, they're some of the longest-lived cells in your body. There's a lot of debate right now about whether you're actually born with all the neurons you'll ever have. But some research suggests that at least in your brain's cerebral cortex, your neurons will live as long as you do. Cool fact number two, they are irreplaceable. It's a good thing that they have such longevity because your neurons aren't like your constantly renewing skin cells. Most neurons are amitotic, so once they take on their given roles in the nervous system, they lose their ability to divide. So take care of them. And number three, they have huge appetites. Like a soccer-playing teenager, neurons have a crazy high metabolic rate. They need a steady and abundant supply of glucose and oxygen, and about 25% of the calories that you take in every day are consumed by your brain's activity. Along with all these wonderful qualities, your neurons also share the same basic structure. The soma, or cell body, is the neuron's life support. It's got all the normal cell goodies like a nucleus, DNA, mitochondria, ribosomes, cytoplasm. The bushy branch-like things projecting out from the soma are dendrites. They're the listeners. They pick up messages, news, gossip from other cells and convey that information to the cell body. The neuron's axon, meanwhile, is like the talker. This long extension or fiber can be super short or run a full meter from your spine down to your ankle. We've got a few different axon layouts in our body, but in the most abundant type of neuron, the axons transmit electrical impulses away from the cell body to other cells. For us students of biology, it's a good thing that nerve cells aren't all identical because their differences in structure are one of the ways that we tell them apart and classify them. The main feature we look at is how many processes extend out from the cell body. A process, in this case, being a projecting part of an organic structure. 99% of all your neurons are multipolar neurons with 3 or more processes nucleuses sticking out from the soma, including one axon and a bunch of dendrites. Bipolar neurons have two processes, an axon and a single dendrite, extending from opposite sides of the cell body. They're pretty rare, found only in a few special sensory places like the retina of your eye. Unipolar neurons, on the other hand, have just one process and are found mostly in your sensory receptors. So if you ever find yourself probing around someone's nervous tissue, remember these three terms to help you figure out what you're looking at. But because we're talking about physiology here as well as anatomy, we have to classify these cells in terms of their function. And that basically comes down to which way an impulse travels through a neuron in relation to the brain and spine. Our sensory or afferent neurons pick up messages and transmit impulses from sensory receptors in, say, the skin or internal organs and send them toward the central nervous system. Most sensory neurons are unipolar. Motor or efferent neurons do the opposite. They're mostly multipolar and transmit impulses away from the central nervous system and out to your body's muscles and glands. And then there are interneurons, or association neurons, which live in the central nervous system and transmit impulses between those sensory and motor neurons. Interneurons are the most abundant of your body's neurons and are mostly multipolar. Okay, it's applied knowledge time. Let's review everything we've learned so far in terms of that spider on your knee. Those 8 creeping legs first activate your unipolar sensory neurons in the skin on your knee when they sense something crawling on you. The signal travels up an axon wrapped in Schwann cells and into your spinal cord, where it gets passed on to several multipolar interneurons. Now, some of those interneurons might send the signal straight down a bunch of multipolar neurons to your quadriceps muscle on your thigh, triggering you to kick your leg out before you even know what's going on. Other interneurons will pass that signal to neurons that carry it up your spinal cord to your brain. That's where your body first recognizes that thing as a spider, and the connections between neurons interpret and split the signal so that you can either scream and start swinging your arms wildly about, or remain calm and with dignity remove the spider from your person. It's all based on the connections between neurons, which brings me to a whole new question. How in the name of Jean-Martin Charcot do nerve cells use chemistry and electricity to communicate with each other? It's one of the most stupefyingly awesome and complicated aspects of your nervous system and basically of all life, and it is what we will cover in our next lesson. Today, you learned how sensory input, integration, and motor output of your nervous system basically rules your world. We talked about how the central and peripheral systems are organized and what they do, and looked at the role of different glial cells and nervous tissue function. We also looked at the role, anatomy, and function of neuron types in the body, both structurally and functionally, and how everything plays out when you find a spider crawling on your skin. Thank you for watching, especially to all of our Subbable subscribers who make Crash Course possible for themselves and for the whole rest of the world. To find out how you can become a supporter, just go to Subbable.com. This episode was written by Kathleen Yale, the script was edited by Blake DiPestino, and our consultant is Dr. Brandon Jackson. It was directed by Nicholas Jenkins and Michael Aranda, and our graphics team is Thought Cafe.
Okay. So that's a brief overview of, kind of the main structure of our nervous system. He's kind of alluding to the fact that, we're definitely going to talk about how the nervous system interacts, which is going to be action potentials. We are going to discuss that as well. But we're not going to watch the big, huge video on it. Checking out chapter 9 here, right? We're looking at this. This got kind of the biggest overview of our sections here, but we are going to be talking about the divisions of our nervous system, right? Your central versus peripheral, different types of neurons that we have, which is funny because then those different type of neurons, like how they actually work. And so those are organized the same way, actually, which is kind of fun to look at. Spinal nerves, and then this clinical aspect stuff, like we're not really going to go over. So let's go ahead and talk about what the nervous system is, right? So the nervous system is a control system for the body that coordinates all body systems, right? So the nervous system's job is really to control everything. That's its main job here, right? Is to kind of do things the way that they are supposed to be done, right? So it's going to not only detect stimuli, but it's also going to respond to that stimuli, right? So it's going to detect and responds to stimuli. If you touch a hot stove, your nervous system is going to sense that, but it's also going to naturally want you to move your arm away. But at the same time, there is like the somatic division that, you know, lets us do whatever the heck we want. We can choose to do something, you know, specifically. And so you have some automatic functions and you have some functions that are totally under your control. And so your nerves will carry messages to and from different centers of the brain and body, right? So now, first we got to kind of look at the divisions of our nervous system here, right? So I usually like to draw this in kind of a flow chart, which is similar to how they put it in the video there, but I think we'll be able to do it just in our notes here. So if we're looking at divisions of the nervous system, we'll go ahead and start by talking about your central nervous system, right? So your central nervous system, I'm gonna say, no, I'm not. Okay, your central nervous system is responsible for coordinating nervous signals, right? And so it's going to, it consists of the brain and the spinal cord, right? So your nervous system, your central nervous system is going to be your brain and your spinal cord. That's this section right here, right? Now, from your central nervous system, it's going to split off into all of these individual like nerves here, right? So these are your spinal nerves. And so like, you know, like let's say this one right here branches off, right? This is in charge of controlling, you know, maybe some of the muscles along your lat. It's in charge of like sensing information there. And so anytime something happens in this realm, it's going to travel through this nerve, get to the spinal cord, travel up to the brain. The brain's going to interpret that information and then send a response back, right? So that's the difference between your central and peripheral. Your peripheral is really in charge of like gathering all the information. If the central nervous system is like a CEO, the peripheral nervous system is all of the company's like employees, right? So the peripheral nervous system are all of your, is responsible for carrying nervous signals throughout the body, whether that's detecting or responding, right? That's going to be both directions. And it will consist of the cranial and spinal nerves. So you got cranial nerves, which branch out from your brain. You got spinal nerves that branch out all over your body. So if you've ever talked to somebody who has like sciatica, right? If we look at like what sciatica is, right? It's a problem you'll hear people describe where they'll get like a low back pain and all of a sudden it'll shoot down their leg. That's how they'll describe it. They'll get like a pain in the, that'll travel down their leg. Sometimes people will feel it, say it's like a burning sensation in their butt that will sometimes travel down the leg. So when you look at like what's happening in sciatica, you've got this one bundle of nerves, this one nerve in particular called your sciatic nerve. And it's right here at the very base of your spine, right? So if you look right here, your sciatic nerve is right here before it branches out all into the different parts of your leg. Now, if you have got like some type of like herniation, right? Like here's a spinal disc and this is a herniated one, which means all this fluid right here is actually pinching out and touching that spinal nerve. This is like a herniated disc, and that can sometimes cause sciatica. But more commonly, a lot of times sciatica can actually be caused, and we call it a little bit different. We call it piriformis syndrome, where this muscle right here, which is a vital part of our anatomy and really responsible for like helping us stabilize the sacrum here, and it allows us to do rotational movements in our hips. But like when you look, if this muscle gets really tight, as often a lot of muscles do, it starts getting pulled into a shortened position, and that can also pinch that nerve. Which is why if you have a client who has sciatica, we will stretch this piriformis muscle, and sometimes that can provide temporary relief. But the reason they get that sensation running down their whole leg is because this nerve right here is getting pinched, which is now interrupting that signal as it travels down the leg, right? So this is very much part of your peripheral nervous system. And if you interrupt that signal, your nervous system, which is in charge of like detecting stimuli, starts to kind of make a stimulus that it really shouldn't be making, like it's like, hey, the butt's on fire. And it's like, you mean there's a match back there? Because that's literally what people will say it feels like. And it's like your nervous system is like, well, I don't know. I can't really tell because I'm being interrupted, So that's where, a pinched version of that. So this is the peripheral section. And then the central section is up top. It's in charge of making the decisions, but if it can't communicate with its workers, right, if it can't communicate effectively with the peripheral, we get all kinds of pains and things and aches and things like that. So the peripheral nervous system needs to be divided down into two more individual sections, right? Because here's the thing, when it comes to your peripheral, like I said, your nervous system's in charge of coordinating everything, not just the stuff that you want to do, but also the stuff that's automatic, right? Like my nervous system is controlling my heart right now. My nervous system is controlling my glands, whether or not it's like hot in my room, if I should be sweating or not. My nervous system is doing all of that, and I'm not really thinking about it. It's naturally controlling my diaphragm. Although, like, if I want to, I can manually start breathing anytime I want. I can take manual control in some scenarios, but for the most part, a lot of things are automatic, which we're going to call autonomic. So your peripheral nervous system is going to split into two primary sections here. You are going to have your somatic nervous system, which is going to be your voluntary nervous system that controls things like skeletal muscle, right? So like skeletal muscle, all that stuff we talked about yesterday. If I want to contract my biceps, my somatic nervous system is going to do that. So my central nervous system will make a decision. It will then ship that decision to the peripheral nervous system, and then the peripheral nervous system, using its somatic function, will make it happen, right? So we're going to label these out as like somatic nerve. We're going to label them out as systems, which works. But it almost helps a little bit to think of them as like function, right? You can kind of think of it as like somatic function versus autonomic function, right? Like somatic function is voluntary. I'm making choices, and so it's functioning under my choices. Whereas autonomic functions are things that happen automatically so that I don't have to think about them. Can you imagine how exhausting it would be if you had to continue remembering to like beat your heart every day? Just like, okay, got to keep going. Like, I need this at 60 beats per minute. Oh, I'm going uphill. I should probably make it beat faster. Let's go to 150. Like that would be super impossible. So then we do have our autonomic nervous system. So autonomic nervous system. Or what if you were like, before you were eating food, you were like, all right, I better make some spit, So that is your involuntary nervous system that controls things like smooth muscle, cardiac muscle, and different glands throughout the body, right? So your autonomic nervous system is in charge of controlling all that stuff that we need to have happen, but we don't necessarily want to have to think about, right? So for instance, like I just said, my favorite version of like, here's a thing where we are going to hack our autonomic nervous system. I want you to picture the last time you had like the world's greatest piece of pizza. I want you to imagine it like very deeply and intensely, like, was it salty? Was it greasy? Like, was the sauce kind of sweet? Was it really, really good? Like, if you start thinking about all those things, everybody who's like listening to this right now should be like, man, like I kind of want some pizza. Like, and your mouth might be salivating, right? You might find that like you've got extra like salivation. That's because it kind of tricked your nervous system into thinking heavily about it. So now it assumes that food's coming in. So it's like, oh, I better get ready, like food's coming in. And then we're going to let it down, unless you've actually got food at home. But that's kind of how your autonomic nervous system works, right? You didn't have to think about that. It's something that occurred automatically. And then your autonomic nervous system is going to go in two different directions. And that is going to be either your sympathetic nervous system, or your parasympathetic nervous system. And so remember, we really like to get things into a place where we can kind of understand them in twos, right? It's either going in that direction or it's going in that direction. This is a classic example of how we have organized our nervous system. Your autonomic nervous system either freaks out or it calms you down. It either does like, it either like responds to a stimulus by freaking out, or it produces negative feedback to get you back to normal. So your sympathetic nervous system are things, it is often referred to as the fight or flight system. It responds by amping up body systems. Is amping not a word? I use that word all the time. Huh. And I didn't know that. And then we've got our parasympathetic nervous system.
What would be the right way to say that?
Amping? Increasing. Like I think it comes from like, using an amp on a
That's really not a word?
I guess not. Yeah, turning up. I should say that. By turning up. There we go. What if I wrote turned up?
Turning up?
Yeah. All right. So it responds by like, turning things on. Your parasympathetic nervous system, I mean, what's fair though is your parasympathetic nervous system can also turn something on, but that something can be something that calms you, right? It can produce, like if you produce a bunch of adrenaline, your parasympathetic nervous system might produce a whole bunch of dopamine or serotonin to calm you back down. So it kind of gets you back to neutral. So this is often referred to as the rest and digest system. So this is the rest and digest system. It returns the body back to normal, right? So for instance, like your autonomic nervous system, let's say like you eat like a big meal, right? So what's going to happen, you probably notice this like on Thanksgiving, right? Everybody always kind of blames turkey. They're like, turkey has tryptophan in it, and your body and your brain makes tryptophan when you're sleeping. And so like a lot of people think that like turkey makes you sleepy, which I don't think is true if I'm not mistaken. I think that like they debunked that for the most part. But everybody does get sleepy after Thanksgiving. Like that is something that still happens. So why does that happen? Well, like your body just brought in a massive amount of calories. And so your parasympathetic nervous system's like, oh man, all right, like we are not going to use skeletal muscle for a little while. We are just going to lay here and I'm going to work on all this food. So it produces all this stuff that kind of calms you down. But if you go out and play like sports, your sympathetic nervous system's like, all right, let's get all the muscle and nervous system like recruited so that we can work as hard and as fast as possible. Like it amps your body up. And that's why like you sometimes get like really high energy before doing something, so those are kind of both something that you don't have direct control over. We do know that like we can control them through our actions, right? Like I can, trigger my parasympathetic nervous system by breathing into my stomach slowly and thinking calm thoughts and clearing my mind, right? But I can also likewise activate my sympathetic nervous system by listening to like a hard rock song that, motivates me and gets me like, pumped up to go to the gym. But that doesn't mean that I have control over those things, like I know what to do to make them trigger, but I don't have direct control over them because they are both autonomic processes. And so a lot of times when you're doing this, you kind of want to think of this as like a flow chart. You're going to get questions that are going to say, something like your sympathetic nervous system is an example of blank type of reactions. And you'll be like, okay, sympathetic means that it's autonomic. Or sometimes they'll ask you like harder versions, which is like, the body is producing adrenaline in response to a stressor. This is an example of a blank reaction. And so what they mean by that is like, okay, first you need to understand like what part of your system makes adrenaline, which is something that kicks the body into overdrive. So you're gonna go, okay, that's my sympathetic nervous system. My sympathetic nervous system is part of my autonomic nervous system. My autonomic nervous system is automatic. That's the option they're looking for there, right? So sometimes you got to follow the flow chart a little bit. Or it might even go 2 levels up. It might say resting and digesting is under the control of your blank system. The direct answer would be parasympathetic, but it is also fair to say that it's autonomic, and it is also fair to say that it's peripheral. So you might get variations on that. That seems really confusing at first, but just remember this little flow chart in your head, right? These are your 2 central divisions. This one divides into these 2, and this one divides into these 2. Feeling good?
Yeah, there.
All right. So let's go ahead and look at that autonomic nervous system, because as much as we as trainers work on the somatic nervous system, where we are doing stuff on purpose and we are doing things that are controlled by our body, we actually do need to understand a good bit about that autonomic nervous system, because it's a huge, huge, huge part of how we actually function. So I'm gonna go ahead and this is gonna be kind of a different section header here. So the autonomic nervous system, right? Its function is regulates the action of glands, smooth muscles, hollow organs, blood vessels, and the heart, right? So that's like a lot of friggin' stuff. It is in charge of so many different things inside the body that we need to have happen like automatically, right? So it's got all these different neurons that do connect to your spinal cords, but it also connects to your effector sites. So when we're looking at those like divisions there, right, that sympathetic versus parasympathetic sections, when it comes to being autonomic, some of that information's coming in and some of that information's going out, right? So fight or flight systems, they respond to scary stuff. Right, like they detect you're being freaked out. If you were to place your hand, if you weren't like paying attention, actually, you know what I should do just for the fun of it. I should have had this pulled up previously, so this may take a second, but I want to show you my favorite example of the nervous system not working the way it's supposed to. There's a clip from a movie, Dr. Frankenstein. Wait, no. Young Frankenstein. Stab. No, that's not it. Hold on. Class is dismissed. There we go. That's got to pull it up. Okay, I'm going to skip to the section of this. This is a great movie, by the way. It's a Mel Brooks movie, and it's a classic example of the nervous system not working the way it's supposed to. I love this clip. Let's see here, where he gets baited. He is the grandson of Frankenstein. He's trying to, just a little backstory. He's the grandson of Frankenstein. He doesn't want to have anything to do with his grandfather's work, but some guy tells him that his grandfather has died and he's inherited all of his stuff. He doesn't want anything to do with it. He wants to be known as a man of science on his own because he is an expert on the nervous system.
Just before we leave.
Dr. Frank
And he gets very upset.
Frankenstein.
Yes.
Isn't it true that Darwin preserved a piece of vermicelli in a glass case until by some extraordinary means it actually began to move with a voluntary motion?
Are you speaking of the worm or the spaghetti?
Why, the worm, sir.
Yes, it seems to me I did read something of that incident when I was a student, but you have to remember that a worm, with very few exceptions, is not a human being.
But wasn't that the whole basis of your grandfather's work, sir? The reanimation of dead tissue?
My grandfather was a very sick man.
But as a Frankenstein, aren't you the least bit curious about it? Doesn't the bringing back to life what was once dead hold any intrigue for you?
You are talking about the nonsensical ravings of a lunatic mind. Dead is dead.
But look at what has been done with hearts and kidneys.
Hearts and kidneys are tinker toys. I'm talking about the central nervous system.
But sir,
I am a scientist, not a philosopher. You have more chance of reanimating this scalpel than you have of mending a broken nervous system.
but what about your grandfather's work, sir?
My grandfather's work was doo-doo. I am not interested in death. The only thing that concerns me is the preservation of life. Class is dismissed.
So that is one of my favorite moments because like his like that's you know, this is just meant to be a comedy, but that moment is great because it's an example of how your autonomic nervous system can protect you sometimes. Like if a stimulus is so intense, it can keep you, that's what like going into shock kind of is. It's your body keeping you from feeling anything. Like he goes bam, and then he goes, what did I just do? And I love it. Like, and then all of a sudden, you know, there's gonna be a wave of pain that comes afterwards. But that is very much like your autonomic nervous system kind of kicking in there, right? Normally, it would respond to that by immediately just freaking out. But in this case, that stimulus is so intense that the right move is to kind of keep you from feeling that pain. Which we've all kind of experienced before, you know, like I know that like you'll see it sometimes with like pediatricians who are giving kids like shots. They'll distract them by like doing something else, and all of a sudden they'll like get them. And the kid's nervous system gets overloaded because they'll be looking at some type of stimulus, and all of a sudden they won't notice like some type of pain that just happened. So it is possible to kind of overload your systems, right? And that's why things don't always work the way that they're supposed to. That was just meant to be fun, by the way, but don't take anything in that video as like a lesson. So your glands, right? So this is a really classic example, right? The autonomic nervous system, your sympathetic nervous system, the sympathetic section is responsible for triggering certain parts of the body to be on high alert, right? You can kind of think of your sympathetic nervous system like that, right? It might recruit your endocrine system to create adrenaline, or it might, for example, it might actually just enhance your entire nervous system and recruit more motor units. That's an example of how your sympathetic nervous system kind of acts in like its action, right? Like you'll notice that like if you go to lift like a super heavy weight, sometimes like if anybody's ever done like max strength lifting, sometimes you'll notice your hands shake a little bit afterwards, and that's because your whole nervous system is just like, what else do you have that's heavy? You know, like bring it on. You know, it gets all turned on, which is why your nervous system can get exhausted. This is why like rest days are so important. And then your parasympathetic nervous system has exactly the exact opposite, right? So the parasympathetic system is responsible for returning the body to a source, right? And so it will generally will have the opposite effect on an organ. So if you've got something that, you know, your kidneys are where we produce our adrenaline, right? So if your kidneys are producing a bunch of adrenaline because your sympathetic nervous system freaked out, your parasympathetic nervous system will get that to create an opposite hormone to calm you down. Okay, so that's the autonomic nervous system. Now let's go ahead and zoom in and look at the structure, the functional unit of our nervous system, which is the neuron, right? Yesterday we talked about the muscular system as a large, and then we got into individual muscle cells. We're doing the same thing today, right? We looked at the nervous system. Now let's go ahead and understand like each of the individual neurons, right? So the neuron is the functional unit of the nervous system, right? They are the cells that coordinate and make up the nervous system. So they are highly specialized in their structure, just like everything else is, in order to be able to coordinate the body via electromobility. chemical signals. So we're going to say electrochemical signals because your body is using sodium and potassium to create like an electric charge, but they're also like, what happens is at the end of your nervous system, it will often release a neurotransmitter, which is a chemical, and then that chemical interacts with certain parts of your body. So one of my favorite versions of this that we show this video in our nutrition class where we talk about caffeine. So caffeine is what is known as an adenosine-like receptor. And so when your body produces ATP, you end up producing a lot of this leftover adenosine, right? That's the A in ATP. And so this leftover adenosine's job, once it's like kind of just floating around, is actually to bind with receptors in your brain in order to make you a little sleepy. And that's why we get tired when we do lots of work, you know? And so when you do a lot of work and you produce a whole bunch of ATP, now all that leftover adenosine binds to your brain and your brain goes, oh man, we did a lot of work. I'm gonna go ahead and take a nap now, you know? Irene, you're going for a run today. It sounds like you've been doing a lot of running. Do you usually like conk out after you're done? I know that I do that on long runs.
Yeah, and you know, strangely enough, like I have less hunger after I run and do the stairs.
So that is also very common and can be explained with our understanding of the nervous system. So exercise is part of your fight or flight nervous system, right? Your body is physically responding to stress, right? So what's the important thing to recruit there? Skeletal muscle, not digestive system muscle, right? Like your digestive system can relax. When you start exercising, and this sounds crazy, but exercise is actually an appetite suppressant. And people always have a hard time believing that because they're like, whoa, 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 whoa. Once I leave the gym, I'm starving. And it's like, yeah, absolutely. Like once you leave the gym, but exercise creates a suppressing effect because your body sends all of its work to skeletal muscle and actually turns off your digestive system. Then once all the work is done being with your skeletal muscle, it can turn that off and go back to using your digestive system. But if you exercise regularly or if you exercise for super extended periods of time, it can lead you to not being hungry afterwards. Yeah, I'm never hungry after I play Ultimate because we play for a couple hours. But I'm
play Ultimate Frisbee, man?
What's that?
You play Ultimate Frisbee?
Oh, yeah.
Oh, sick.
That is my favorite sport of all time.
Yeah, pretty cool.
Yeah, do you play?
I mean, I've never played seriously, but like in high school, we'll like play sometimes, you know?
Oh, dude, yeah, we'll have to have you out. Like once our game gets back going, we're on COVID pause, but yeah, I've been playing with the same pickup group of guys for like close to 7 years now.
Oh, nice.
Yeah, so it's awesome. And then we play in different tournaments and stuff around the city. So we'd love to have you out.
I was curious, what causes like a coffee crash?
Yeah, so that's kind of how exercise kind of suppresses the appetite. But let's go looking at like caffeine, right? So caffeine, what it actually does is it actually binds to those adenosine receptors because it's shaped very similarly to adenosine. A molecule of caffeine and adenosine look really, really similar to each other. So when you drink coffee, it actually gets into those receptors in the brain and it blocks adenosine from being able to bind. So that keeps you from getting tired. Like adenosine's job is to make you tired. If you can't bind adenosine, you don't get tired. But eventually what ends up happening is your brain is like, well, I've got all this extra adenosine floating around. I should make more receptors. So then you'll need more and more and more coffee over time as you sort of get used to that caffeine effect. Because your brain will make more and more adenosine receptors. And then why do you have like the coffee crash? Well, once that caffeine like kind of, gets out of your system, it's not so much that you have created more adenosine. It's just that all of that adenosine that you had created from before can finally bind. And so like normally you would have gotten like 5 here and 5 there and 5 here and 5 there. But now it's like 5, 10, 15, 20 units are just sitting around and then all of a sudden the caffeine's gone and you get hit hard,
Oh, yeah.
So it's not that coffee like crashes you or makes you more tired. It's just that you're getting all of the tiredness that you normally would have spread out. So it feels very intense.
Okay.
The neuron, if we're looking at it, it is highly specialized in its structure. Every cell is specialized to its structure. We know that's how cells work, right? But it's going to consist of a couple different things. One of those is going to be the cell body, right? So the cell body is going to contain your nucleus and other organelles. That's not surprising. Every cell is going to have those things. But you're also going to have cell fibers, which are special to the nervous system. And these are things like dendrites. So dendrites, actually, we'll put this up here. Cell fibers are, you know what? Hold on a second. Nervous cell body. I think that's going to be a little clearer. The nervous cell fibers. Which are specialized, oh boy, fibers specific to the nervous system cells. That'll work. Okay, so cell fibers that you have are specialized specifically to the nervous system. These two things are going to be called dendrites, which are fibers that carry nerve impulses to the cell body, right? So they act as fingers and, or as we'll say arms that attach to and synapse to other structures in the body or to other neurons. So dendrites are basically these big fingers that stick out from your nerve cell, right? And so that makes them really good at grabbing onto other things and like pairing up with them, right? Like synapsing with it. And then the axon is also very similar, but it's this big long tail. It's sort of like one central dendrite that ends in like a little branch. So an axon is going to be fibers that carry impulses away from the cell body, right? So the dendrites gather the information, take it to the cell body, and then the cell body sends it down the axon. So now that impulse is going away from its central section, right? And so this acts as an arm that will synapse to other structures as well, but it's moving away from the cell, right? So dendrites are heading towards and axons are heading away. So here's what that kind of looks like. By the way, dendrite, I think it comes from the word tree, if I'm not mistaken, and you can kind of see it does look like branches, right? So all these individual little fingers sort of grab each other, right? So I might have the axon of one neuron that attaches right here, and I might have an axon of another neuron that attaches here, and another one here, and another one here, here. Millions and billions. There are so many neurons in your brain. One of my favorite weird facts, there are more neurons in your brain than we have discovered stars in the sky yet. Not saying that there are more neurons than there are stars, but there's definitely more than we can see yet. Yeah, question.
Brett, is that what you can take apart and you can go around the world like 3 times with your?
Oh, your nervous system? Yeah, I think so.
Yeah.
I'm sure. Yeah, absolutely.
It's like I can't wrap my head around that. How much?
90,000 miles. Yeah, if you were to stretch them all out.
What the hell?
Yeah, and then let's see here. What is the circumference of the Earth?
5'10".
Yeah, right. 24,000 miles. So 90,000 by 24,000.
That's just nervous system.
Yep. That's just your nervous system. Let's see here. How long is the? God dang it. Oh my God, I can't believe I can't think of this word. Vascular system. Your blood vessels are also really long. They can make up about 60,000 miles. And that's how small your blood vessels are. They are tiny. Make no mistake.
It's incredible.
Pretty cool, right? So little itty bitty things. So here's what's really cool about your nervous system. These are physical things. I'm definitely going to talk about this more in just a little bit, but like when you get like a nervous system signal, if it travels from like this neuron and it connects right here and then travels down, right? That is a different signal than if it traveled from the same neuron over here, but then rather than connecting here, it connects to this one. This little tiny slight difference means it's a completely different signal. One might be something that tastes sweet and one might be something that tastes salty. So how the heck do we like recruit those things? How do we like recruit our nervous system in such a way to create like coordinate different signals? Well, that's what your nervous system does. It finds more and more efficient routes to travel. And that's how we get better at stuff. So like, let's say you're standing on one leg, right? Like you're balancing like this, right? You're just kind of slowly gaining your balance. And so you're getting all this different like stimulus. Like my brain's getting information from here, it's getting information from here, it's getting information from here, it's getting information from here, like all those bits of information. And it's testing like, okay, well, if I'm here, what happens if I recruit, you know, the obliques for this many pounds of force, and I recruit the low back for this many pounds and the foot for this many pounds. And then all of a sudden I tilt back here. It's like, okay, well, that was too many pounds of force. And then all of a sudden, like once I'm back in this position, it's like, oh, I remember that position. What if I recruit, last time that didn't work, so what if I recruit for this many pounds of force? And then finally, it figures out that's enough to get me back to neutral. That's how your body slowly figures out like how to develop what we call proprioception, which is arguably one of the most important terms that we ever are going to talk about. Proprioception is your body's understanding of where it is in space. And we're going to do a whole lecture on it. But that is thanks to neurons, right? Their structure allows them to let your nervous system slowly figure things out because it gets more and more efficient at traveling down, you know, this section to that section to that section. That's the difference between your thoughts. By the way, there's what your nerve cells kind of look like. This is the nucleus here. So when you're looking at that, right, when you're looking at like these different signals and you're trying to understand like how they work, think of them as like physical things, right? When you're training, let's say you're trying to like max out on a barbell squat, right? You lift really heavy, your nervous system slowly figures out how to recruit your quads, your hamstrings, your glutes, and like stabilize your core, and it gets better and better and better at the movement. Meanwhile, maybe you do experience some hypertrophy as well, but you're getting stronger both from like more muscle mass, but you're also developing a stronger nervous system that knows how to coordinate the movement more efficiently. And that's why we need to not only train our muscles, but we also need to train our nervous system. I'm kind of getting ahead of myself a little bit. Let's get back into just looking at the anatomy here. So on your dendrites, on your axon is going to have these specialized structures called the myelin sheath, right? Which is a special type of cell that insulates and protects axons so that nervous system signals don't get lost, right? Or don't dissipate in between. We got to remember that, like I said, this is all like an electrochemical signal. So what you'll see is you'll have these specialized cells surrounding your axon. Like if I go back to the axon over here, see these little like bulges that are around the outside? That's a little bit of myelin. So there's these myelin sheaths that are kind of protecting this signal. So the signal travels, you know, from a dendrite and then it gets to the central body and then it travels down. We don't want that signal to randomly get lost. You know, there's a lot of fluid running around in the body and electricity loves to run through fluids. So the myelin sheath is very fatty. And so that fat insulates that nervous system signal and keeps it from leaking in either direction. Now, that's not always true for everybody. Some people have a disease called MS, right? Multiple sclerosis. And what happens in multiple sclerosis is the myelin sheath actually gets damaged. If we look at it, what ends up happening is for some reason, their immune system actually eats away and damages that myelin. And so you'll end up having like a little bit of exposed axon here, and that causes a nervous system signal to get lost. Now, luckily, we know it's a series of signals that controls our nervous system. It's sort of like zap, 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 zap. So there's another signal coming along afterwards. But often what you'll see with somebody who has MS is it looks like they have really bad balance, or they have like a lack of control in their muscles. They'll be walking along, and then all of a sudden their leg will give out, and then they'll catch themselves and keep going. And that's because they lost that signal for just a second. But then, the next signal maybe came around afterwards, or maybe they recruited like a different muscle to kind of catch them. Right. And that's actually where our job comes in when we're working with people who have MS. We know that we can't cure MS. We don't know what the cure is, but we do know that if you exercise and get better at balancing and you learn how to catch yourself more effectively because you're more coordinated, that can improve your quality of life if you do have this disease. We can't cure it, but we can make life better, right? Same thing is true with diabetes. We can't cure diabetes, but we can get your body into a place where it controls your blood sugar levels, which, is kind of a cure actually, but okay. So that's the section of our neurons. But now we need to look at types of neurons, right? So types of neurons. And this is going to be kind of funny because you're going to see some serious similarities between our types of neurons and our function, which makes a lot of sense when we go back to that form following function. So you have got sensory neurons, which, and by the way, I got to apologize because we are going to use the terms afferent and efferent a lot, which is going to sound really similar. So hopefully that comes across on the friggin' Zoom call. But sensory neurons are known as afferent neurons. And these are neurons that conduct impulses towards the brain, okay? So these are neurons that conduct impulses toward the brain, right? So their job is they go from an effector site towards to the brain. Okay, that's a sensory neuron. Their job is to gather information, right? Responsible for gathering information. Okay, then we also have motor neurons. And these are your efferent neurons. Right, these are neurons that conduct impulses to muscles or glands, right? That's impulses away from the brain, right? That's a good way to think about this as well, right? This is, as impulses are, you're gathering information. We need to get that information to the brain. Well, now your brain needs to get the information back, right? So that's where your motor neurons come in, right? Hey, I've been stabbed, right? Your sensory neurons are responsible for that. And your motor neurons are all right, well, let's walk to the hospital, right? They're sending information to the body to recruit your muscles. So they go from the brain to an effector site. Okay, they are responsible for sending information information away in order to recruit muscles. Okay, and then we have interneurons, which are all the interneurons in between. Right, and these are neurons that relay information from place to place. Right, so that's going to be one neuron to the next neuron to the next neuron. Okay, for sending information from neuron to neuron to neuron. Okay, what's up, Irene? Question?
Yeah, so when your foot falls asleep, what's happening there with the
Yeah, totally. This is so funny. We just talked about this yesterday, actually, before the call got started. And remember yesterday I said, I was like, I'm going to bring this up. When your foot falls asleep, right, you get this like super intense tingly sensation that you slowly realize. And you didn't know your foot was asleep until it was too late, right? Like you didn't notice it until it started the tingling. And you're like, oh crap. And then you step off your leg and then you're like, oh, wait for it. And all of a sudden it's like, ah. So what that is it's not that you are cutting off blood flow to your leg. A lot of people think that it's like suddenly, you pinched your blood flow. And so you're experiencing that. Luckily, that is not true. If that was true, your foot would suffocate and die. And so you would be left without a foot afterwards because your cells wouldn't be able to produce ATP and then they're kaput. So luckily, that's not what's happening. But what is happening is that you are sitting on your nervous system. And so like these sensory and motor neurons are losing their ability to communicate with each other. And so like information's not coming in and information's not going out. So your brain is like, hey, is my foot still there? Right? Like it's not getting information. So it's like, hey, are you still there? It's kind of like in these Zoom calls when all of a sudden it gets too quiet. I'm like, you guys following? Like I have to like send a signal out to make sure that like people are still connected. That's exactly the same thing that's happening. Or like when you're talking on your cell phone and it just goes quiet and you're like, you still there? Right? And you think that maybe somebody literally fell asleep on the other side of the phone. That's what your brain is doing. Your brain was like, hey, foot, like, and it's sending a big signal. All of a sudden you finally notice that signal. And so then you're actually experiencing all of that pinging that your brain is sending. And then your foot sort of goes, ow, 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 and it kind of hurts. And, you're like, oh, it feels terrible, right? And that's your brain going, okay, is the foot still, is he there? Are you there? Are you there? Okay, great. Like, we're still there. Awesome. And then that signal dissipates. But that's what's happening when your foot falls asleep. It's your brain checking to see if the foot's still there. Does that make sense? Oh, did I lose you guys? See? Actually, oh my God, we did lose Raul. Okay, so neuroglia. So this is our next little bit that we've got. We do have these really cool like neuroglia. This is actually kind of fun. I think he mentions in the video about how like we oftentimes didn't know what a lot of this stuff does, and we're still kind of discovering about neuroglia. That is definitely true for me as well. Like I remember like, being told that this stuff didn't really do much. It was just there to kind of protect and repair things. But what's interesting is like it can even it can actually take over and act as your nervous system if your nervous system ever gets damaged. We'll see that sometimes in paraplegics or people who are victims of stroke, And so examples of this are things like your Schwann cells, right? So for instance, like that myelin sheath that I talked about earlier, that's an example of like a Schwann cell, but also things like oligodendrocytes and astrocytes, which are basically these little things that connect. They look like stars, that's why they're called astrocytes. They actually connect your main central like nervous system to other materials. And so then they can send signals as well, but they don't quite do it in the same way. And we still don't, I'm definitely no expert on neuroglia, but it is kind of fascinating to me that like we're finding that they can actually take over when other parts of your nervous system has been like inhibited. All right, so let's look at so we got our types of neurons, right? We got our sensory neurons, we got our motor neurons, we got interneurons. This is kind of cool because this very much is similar to how our nervous system actually works, right? Like we know that our nervous system works with a series of like electrochemical signals, right? But if we're looking at like how that works, we got to understand like these different junctions, right? So looking at the nervous system at work, right? Your nerves are going to sit at a resting state when they're not doing any work, right? So basically everything is going to be polarized. I'm going to pull up a picture of what this looks like, right? This is a polarized section. Don't pay attention to this over here, but this is polarized. And when I say polarized, I mean they are polar opposites, right? This is negative and this is positive. This is a resting state for your nervous system. So what your nervous system does is it actually keeps sodium on one side and potassium on the other. It keeps those two things separated. And those two things have different levels of charge. Sodium, for instance, is more negative than potassium is, right? And so because of that, when you have a whole bunch of sodium on one side and you have a whole bunch of potassium on the other side, you have a negative end and you have a positive end, kind of like a pair of batteries, right? So your battery has like a plus side and it has a minus side. If you keep both of those batteries in the same direction, they don't do anything, right? Like it doesn't create any charge. But if you flip one of those batteries and now you have positive here, negative here on this one, but you have negative here and positive here on the other one, right? That is going to create charge. That's going to create electricity. Your nervous system does that by polarizing using sodium and potassium. So luckily we have specific pumps that can push sodium and potassium in the opposite direction of each other, right? And what that does is that creates that electric signal. So it'll basically let batteries sit like this when nothing's happening. But then as you want to coordinate a signal down a neuron, it'll flip and that creates a little bit of charge. And then it'll flip it back and go back to resting. And meanwhile, that signal is going to travel down. So it might go from this section of the neuron and it creates charge. And then over here, you know, it goes like this and then it flips it back. I'm going to try and be coordinated with my hands here, but it kind of looks like that as it travels down a signal, right? So here's what that actually looks like, right? What will happen is we've got our positive stuff outside the cell and we've got our negative stuff inside the cell. So there is more sodium outside and more potassium inside, right? But then what happens is a stimulus occurs and a whole bunch of sodium enters your cell, right? So a stimulus such as like you choosing to recruit your muscle, or a stimulus such as cold air walking, blowing over you, some type of stimulus occurs. I think the example that he uses in the video is like a spider touches your leg, right? So what's going to happen is a whole bunch of sodium is going to enter that nerve cell. And that is going to cause depolarization. So now they are going to flip. You are suddenly going to have more negative stuff outside and more positive stuff inside right here, which nature hates, right? Remember nature hating gradients, right? Nature doesn't like it when things are, mixing. And so it's going to try to separate things back to neutral gradients. So what's going to happen is potassium is going to leave. Right? In fact, so much of it's going to leave that you'll often go through what is called hyperpolarization, where it'll actually drop just below what it's supposed to. But then those concentrations will restore back to neutral, and that's the end of that signal. You might notice this looks kind of similar to like that EKG machine in a hospital, right? The beep, beep, right? That machine is measuring this happening in the heart, right? If we look at an EKG, there it is, right? Like the signal goes whoop and it drops and then it goes back up. It kind of looks like this. That's your heart. It's got a little bit of an extra wave because like it looks ever so slightly different in the heart because the heart actually has channels that leak on purpose. Normally your nervous system has channels that require ATP to kind of pump things around. Your heart pumping actually changes the shape, which allows it to polarize on its own. It has these leaky channels. Whereas like your nervous system doesn't leak, so it chooses to open them up and push something in the direction it needs to go. And then, once those things are restored, that's the end of that signal. But another signal is going to come along right afterwards. And that's another way that we control strong contractions versus weak contractions, right? Strong contractions are when you send signals super fast like this. Right, that's a powerful contraction. Like, there's just sodium, potassium, boom, 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 right? One signal, another signal, another signal. But a slow contraction, or I'm sorry, a slow frequency of signals is a weaker contraction. So if it goes, right? Notice how like the volume of those two, like, this, same volume, right? I can't contract harder. I can only contract for a certain amount of electricity. It's always the same. But the difference is how fast I recruit that signal. If I recruit it really fast, that's a super powerful contraction, resulting in lifting super heavy weight, right? And if I contract it really slowly, that's a much weaker contraction. So now we're starting to understand, if we go back to yesterday's lesson, the difference between strong contractions and weak contractions, right? If I'm training for maximal strength, I want to recruit my nervous system fast, right? And I want to recruit as many motor units as possible. And if I want to have a weak contraction, I'm going to recruit less motor units, and I'm going to recruit those signals slowly. And that's how you have a difference between strong contractions and weak contractions. By the way, this is just meant to show you sort of what that polarization looks like, right? So it's like positive, 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 and then all of a sudden it flips it, and the positive goes inside. And now that electricity is going to travel. So it's going to work its way down in this direction. So you can see here it is, like returning back to normal as that signal travels down. Now, your myelin sheath is actually really important here. All that myelin protects that signal from leaking out or getting lost, right? It keeps that electricity from going where it needs to, but it also actually allows your nervous system to travel even faster. Because there is a little gap between your myelin in each of these, there's this really cool little leaping action that occurs from like the very end here to the very end here. And that is called saltatory conduction in this little gap right here. And so those little gaps are called the nodes of Ranvier, and it's where the electric signal jumps from one spot to the next, okay? So that is an action potential. Now, there are also synapses, right? So now what happens when you get to the very end? Well, when you get to the very end of a neuron, it's going to synapse with some other type of cell, right? So you're going to see the axon, that's going to be the tail, and it's going to release a neurotransmitter, just like yesterday we talked about acetylcholine, right? Into that synaptic cleft. And if it goes into like another neuron, it'll just attach to that neuron's dendrite and then send the signal on the next, to the next neuron. So if it's going neuron to neuron to neuron, it's going to, synapse and use acetylcholine that way. But if it's going from like neuron to muscle, maybe it uses, acetylcholine to create that contraction within the muscle. But there's other neurotransmitters as well. What happens if you get to the end of your neuron and it releases something called norepinephrine? Well, that is your adrenaline. And so that's going to amp up things like skeletal muscle and create like, those types of hormones. What if it releases serotonin? Well, that's going to be the thing that kind of makes you sleepy and calms you down. Or what if it releases dopamine? That's going to be the type of neurotransmitter that makes you feel, positive and happy. Or acetylcholine will create like muscular contractions. So there's a lot of different neurotransmitters running throughout your entire body. But here you can actually see how one neuron is interacting with another neuron, right? Again, this is a synapse, right? So it's going to travel down, release that neurotransmitter. That's going to land into a receptor site, and that's going to trigger the signal in the next neuron. And so what we need to understand about that, what I think is so cool about the nervous system here, is that that signal traveling, right, is what determines what thought, feeling, or action you are creating. At the end of the day, they're all the same signal. They're all like this negative 70 millivolts electric signal that occurs. But the difference between something tasting salty and the difference of something tasting sweet is the fact that it traveled down different neurons. Now, we can understand that. That helps us understand things even like addiction. Because here's the thing, that's all electricity, right? And electricity burns the crap out of stuff, Have you ever when I was a kid, my parents had this really old vacuum, and I remember plugging it in, and I got shocked really bad, and it like flew me across the room almost. But what it did is it also like lit the freaking plug on fire, and so there was all this like burnt, like all the paint on the wall and the plastic was a little melted from where like super intense heat from like that electricity had damaged the socket. That's what happens when you run electricity through something. It burns it as it goes, right? Well, the more often you send the same signal over and over and over and over again, your nervous system gets better at sending that signal because it gets more and more and more burnt into those neurons. And that's how we get better at stuff, right? That's how we actually get better at doing squats. We do it for the first time and our body's like, how the hell do you do this? And then it figures out the right path. And then the more you do it, the better your brain gets at it because it gets more and more and more burnt in. It's like a groove that starts to form, And so that's a big part of understanding the nervous system. And that's part of like why our addictions are so hard to break, because your nervous system doesn't want you to stop eating sweets. It's really good at eating sweets because it got used to burning those signals that transmit sweet information to the brain. Your body doesn't want you to stop drinking caffeine. It got really good at enjoying the signal that sent caffeine to your brain. Your body doesn't want you to stop playing video games. Your body doesn't want you to stop, procrastinating and being on your phone and reading Facebook and Instagram. Your body gets really good at those things, and that's why those things are so hard to break. It's difficult to do something that you've never done before because you have to figure out which neurons to travel that information down, and that can be exhausting. Your brain would much rather do something that it's good at because it's easy. So
Brett,
yeah, go ahead.
so it creates more like pathways, and does it kill the old pattern, or how
No,
does that?
that's the thing. That's why it's so hard. That's why it's so easy to return to old habits. Because once that pathway is created, yeah, it's your brain's going to remember how to do it. This is also why if you haven't ridden a bike in 25 years, you can just hop right back on, and you don't really forget how to ride a bike, right?
Right.
That's why that works. Now, whether or not that thing is addicting is up for debate, but I mean, I guess it depends on the person, right? But like, yeah, that's the thing. You creating a new neural pathway, but it's not like you can't create a different pathway that is in some ways more addicting. Like you can. This is why so many people replace bad habits with things like exercise. They still get to feel like really positive, but they're doing it in something that's like healthy and not destructive.
And it's also sending signals to different parts of the brain as well, Brad, when it's like when you change and shift into something else.
Yeah, different parts of your brain control different things inside
Mm.
throughout your body. Like you've got your motor cortex, you have got like the your medulla oblongata, which is where like a lot of emotion is held. Like different parts of your brain control different parts of your nervous system. Yeah, and we aren't going to spend too much time talking about that. That's definitely not like an area that I'm an expert on. I tend to be pretty good with the nervous system as a whole, but yeah, like when we get into the different parts of the brain, yes, certain parts of it control certain things, and even if a certain part of your brain is damaged, another part will take over. You'll hear about that sometimes where people will have strokes, and people will say their entire personality shifted. That could be true. Maybe the affection part of their brain was destroyed in that stroke. So then the more logical part of their brain started to take over, or vice versa. Sometimes you'll hear people who are very, very logical, and then they'll experience traumatic brain injuries, like they'll be in a car accident or, some type of work-related accident, or they'll have a stroke. And then all of a sudden they become amazing painters, and they never knew how to paint before, but now they're like this amazing artist, and that is because different parts of your brain can create different neural pathways. There's a lot of fun stories about that. Okay, so let's go ahead and quickly look at the reflex arc here. So we know that we have receptors and sensory neurons, we have interneurons, we have motor neurons, right? So when you look at a reflex arc, so if we're looking at right, we're going to see a sensory neuron will gather information, right? And then what will happen is that is going to travel to your central nervous system. So then that signal travels to the CNS, right? And then the CNS coordinates a response, and then that signal travels from the CNS to the motor neuron, and the motor neuron recruits an effector site, such as a muscle, in response. I guess that's the end, right? So a sensory neuron gathers information that travels to the central nervous system. The central nervous system chooses how to respond and then sends that response from the central nervous system back to a motor neuron, and then a motor neuron recruits the muscle in order to respond to it, right? So here's the example, right? This person's touching like a sharp spike, right? And so that spike send the receptors in the finger travel up into the central nervous system. The central nervous system sends it back and recruits the bicep to pull the arm away. Does that make sense?
Shit. Oh, yeah. So even just blinking your eyes, that's happening. All
Totally,
that.
yeah. Some of it's happening autonomically. Yeah, your eyes are kind of your eyes are. There's no such thing officially as semi-autonomic, but that is like semi-autonomic, right? Like sometimes you'll blink. You know, if you bring something close to your eye, like you'll start twitching, right? In response, and the reason you're doing that is because like sensory receptors on like the very ends of your eyelashes are feeling like, you know, air pressure move around, and that's so imperceptible to like our conscious brain, but like your autonomic brain is like, something's getting close, you know.
Yeah.
That's like I love to talk about like the weird anatomy of cats. I think they have such an interesting nervous system. But yeah, cats, right? That's why they have whiskers, is because they're picking up like electric signals through the air, and that's how they're so good at like navigating things. Is like they know how to like move away instinctively. Your brain does
Yeah, you know,
too.
that's part of the reason why I changed my cat food dish, because I noticed she always left, like, because I make her own wet food and they always leave a little bit. I'm like, why is she wasting food? So I changed it to like a flatter plate that
totally
gives her room for the whiskers, and she finishes everything.
That's great. That's super smart. Yeah, that's a super smart thing to do. She was getting annoyed because she was like, God, ugh, you know.
Like, yeah, because they have to fit through, like when they go through a door crack or something, right?
Absolutely.
Their whiskers are as wide as their body size, where they'll be able to fit through back out.
That's so awesome. That's super smart.
And they have more bones, like 20 some more bones than we do, right?
I think so. I'm not 100% sure. That one's over my head.
Yeah. That was one of those fun facts I saw at my vet. For sure they do.
Yeah. Okay, so let's talk about really quickly simple reflexes, because that was, you know, we've got simple reflexes and we've got complex reflexes. Simple reflexes are reflexes that are simple, rapid, and automatic, right? A good example of this is like a stretch reflex. Right? So when a muscle is rapidly stretched, the nervous system sort of panics and recruits the opposite muscles that pull that muscle, that pull in the opposite direction. Actually, not the opposite muscle. But when a muscle, when the nervous system sort of panics and recruits that same muscle to contract so that it shortens the muscle and keeps it from stretching further. Right? So that's an example of a stretch reflex, right? A stretch reflex is where when you rapidly stretch a muscle, your nervous system goes, whoa, too much stretch, too fast. And so it recruits that muscle to take the stretch away, right? For instance, like my pectorals stretch when I go like this, right? So if I were to throw my arms back as fast as I can, my nervous system will actually freak out for a second and contract this muscle back this way. In response, so that it doesn't overstretch the muscle and I don't tear something, right? This is like an example if you've ever been like trying to like bend over and touch your hamstrings and you notice that like your knees buckle, right? That buckling sensation is your nervous system contracting your hamstrings to bend the knee to take the stretch away. which is why we want to stretch very slowly so that we don't activate that stretch reflex. The classic other example of a stretch reflex is hitting somebody on the knee, right? You know, when you go to the doctor, you can still see me if I sit here. You know, when you go to the doctor and they do that thing, where they like, you know, kick your knee forward, they're testing your reflexes. So your quadricep tendon runs down your thigh and then it inserts on your shin right below the kneecap. So your Golgi tendon organ is right here. So if I hit my Golgi tendon organ really, really hard, my nervous system thinks that I basically just stretched my quad like this, but it thinks that I stretched it at like 100,000 miles an hour. So it goes, oh my God, you're gonna rip the quadricep in half. So what it does is it contracts the quadricep from a lengthened position into a shortened position, because that's very safe. Like a shortened position can't be over-torn, right? You can't tear me in half if I'm like this. And so then that contracts the muscle, and that's why the leg kicks forward. You can get a stretch reflex all over your nervous system. Like if you were to poke a Golgi tendon organ really hard, really rapidly anywhere, that's gonna cause that muscle to contract. And that's what a simple reflex is. And that is about it. I actually thought we were gonna get into the functions of the nervous system, but I guess we're gonna get into that tomorrow, actually. All right, let's go ahead and wrap this up with a little bit of endocrine information. This is gonna move very, very quick, even though there is like a lot of there's actually a lot of slides here, but there's not a lot of information that's relevant to us. So if we're looking at the endocrine system, this is also a control system in the body, right? But this is a series of glands that produce hormones in order to control various body systems, right? So it works with the nervous system to control and coordinate all other body systems, and it affects the body via chemical stimuli. So, you know, so before we were looking at the nervous system, when it wants something to happen, it zaps you, right? The endocrine system, when it wants something to happen, it saturates you with chemicals, and those chemicals make something happen, right? So they're chemical messengers, right? So that's what a hormone is, right? A hormone is a chemical messenger with regulatory effects on cells or organs, right? So that's its main job here, right? So they're released through these ducts. Some of the most common ones are going to be things like growth hormone. Growth hormone is really important because that actually triggers your cells to divide and grow. You were talking about autophagy earlier, right? Growth hormone is a big part of that. Thyroid hormone, that's one that controls like how quickly your cells produce energy and things like that. Insulin targets like pulls sugar out of your blood to produce ATP. So like hormones affect your tissues in a lot of different ways. But here's the thing about hormones. Hormones work they kind of work like, you know, on like a hotline. There's like a hormone hotline running throughout your body, right? Like what'll happen is you'll get one hormone, which triggers the release of another hormone, which triggers the release of another hormone. And now finally you get the effect that you were aiming for, right? Which is kind of weird. And that's actually why your hormones are so slow to respond. And it's also why teenagers are so hormonal. Like teenagers will be so angsty, and that's because like their body is producing new hormones that kick into place like through puberty, and their body is like, how do I control these freaking things? Oh God, there's so much running through it. And then all of a sudden there's nothing. It's like, now I've got nothing. And so your nervous system just feels really unstable. And eventually it's, you know, kind of learns how to control all that and stable out. But that is what we talk about. So you have things like thyroid stimulating hormone, which is TSH. Thyroid stimulating hormone is a hormone that stimulates the release of thyroid, and then thyroid stimulates different tissues. You've also got adrenocorticotropic hormone, or ACTH, right? And that is a hormone that triggers the release of cortisol, or it's a hormone that triggers the release of adrenaline, right? Like these are both like, it's a hormone that triggers the release of a hormone, which triggers the release of a hormone. So that is sometimes why this is so hard to control. Certain hormones, sometimes you'll get a really dangerous thing happen, which is called a cascade. Like a cascade is basically where you'll create a hormone and then that'll trigger the release of another hormone, which might can trigger the release of another hormone. And then finally, whatever you wanted to affect is affected. But this original like creator of this hormone might not have gotten the signal, like because it took a little while for it to get affected, it might make more of that hormone. So then like this thing that you created finally affects the system, but now there's another wave coming afterwards. And so your body goes, oh shoot, I didn't want to control that anymore. I wanted to slow that down. So then it produces an anti-hormone. But by the time that happens, and then you might create too much, and then all of a sudden it dips too low, so then your body makes more of the other one. So it's just like you end up making all these hormones to control your other hormones. It's like if you've ever been painting and you've been like mixing paints to like get the right color, but then you're like, I used too much blue, so then you add more yellow, and you're like, that was too much yellow, and you add more blue, and you're like, God, and it's just like, it gets all out of whack, and so that can sometimes lead to what is called a cascade, and cascades can be really dangerous because it can lead to your body overdoing it, and that can even lead to a very, very dangerous, very severe thing called a thyroid storm, which is basically where all these hormones are just running rampant throughout the body. Yeah, sorry, Irene, you had a question. What's up?
No, that partially answered my question, because with the thyroid, there's hypo and hyperthyroidism, where so what originally screws up the whole circulation of the signals?
You also got to remember this is all under the control of your nervous system, right? Which we know gets better at doing things the more often you do those things, right? It gets more and more burnt in. So stress can physically change your brain. When you are more and more and more stressed, right? You're creating your nervous system creates a signal to coordinate the release of stress hormones. And then the nervous system gets more and more burnt in and gets used to making that signal. Meanwhile, your hormones are excreted by glands, right? Actually, I'll put that up here as a definition here, right? So glands are excrete hormone, are under the control of the nervous system. Or actually, no, I don't want to say that either. I want to say recruited by the nervous system. Recruited by the nervous system to release hormones, right? So glands are where you get your hormones from. You get a gland right under your tongue. Like if you stick your tongue, you bend it down and you poke it, it'll spit out some saliva, right? Those are your salival glands, right? You could also do it with your finger, right? You could just like lift your tongue away and poke it, and it would release juice into your mouth. So your nervous system recruits these glands, right? It does that. But also, like, sometimes you'll have people who have hyperthyroidism, or they'll have like a pituitary disorder. Your pituitary gland is what we call the master gland. It's the main one. And actually, I'll put that up here as well. So the pituitary gland is the master gland. It controls the release of certain hormones. So your pituitary is actually responsible for recruiting that. So when you have hyperthyroidism, right, that is where your pituitary gland is unfortunately recruiting way too much thyroid hormone. And that's located back here, actually, on the back of your esophagus. And so there's too much thyroid stimulating hormone running through your body. And so it's just making all of your body systems run at like super high speed. And so you're burning through energy like crazy. Hypothyroidism is exactly the opposite. Your body's not producing enough thyroid stimulating hormone. So then your thyroid's not being stimulated, so your body's not producing energy very quickly. So those are sort of how that works, and they're under the control of your nervous system. But remember, your nervous system, like if you get good at recruiting things, it starts recruiting those, and those glands can actually experience hypertrophy as well. You know, like these are physical things. So if your nervous system gets good at it because the signal's traveling easily, and the gland starts to enlarge where it starts producing more and more of those, you know, juices, those hormones, now all of a sudden like stress has changed your brain. And this is why we all know somebody who's so good at stressing out. And we know some people that like you could shoot them in the arm and they'd be like, oh wow, bummer. You know, like we know, you know, people on both sides of that spectrum. There's a great female comedian named Aparna Nancherla. She's got this great bit where she's like, she was talking about how she went to Hawaii and she was like jumping into this lake. And there were these people who were just way too relaxed, like these surfer dudes. And he was like, she was like trying to get, she's a very anxious person. She was like trying to work up the courage to like jump into the water. And these guys were like, come on, you just got to relax and do it. And she's like, and one of those guys' face was physically bleeding. She's like, that is a sign that you do not have enough stress in your life. And I love that joke. Like, she's like, I jumped into the water just to get away from those weirdos.
Wow.
Yeah, like she's somebody who has like a lot of stress. I'm like, these guys are clearly just like way too relaxed. But that is, your nervous system will change. Like my mom is a stressed person. I guarantee you that is what led to her heart attack. She doesn't know how to let things go. My dad and I always make the same joke. My mom and I, you know, we'll like leave the house and my mom will go, did I leave the stove? Did I leave the gas on? And it's like, Mom, our house is electric. You know, like,
Yeah.
That's who she is. She'll find something to freak out about. So those are what hormones are. They're excreted by glands and they're under control of this main one, which is your pituitary gland. Now,
thank you for that thorough explanation.
Yeah,
it was very helpful.
Oh no, it's good because we really don't talk about hormones very often. It's a small part of our job, but it's a big part of our body. Hormones are often responsible for negative feedback, right? Going back to negative feedback here, your endocrine system will over-secrete like a specific hormone, and then that tissue becomes too active, right? This is kind of describing what I just talked about. So then tissue negatively affects that gland in order to decrease that secretion. So sometimes like that tissue will push back and say, no, I don't need that much. And so that will decrease your secretion of that hormone. That's how your body gets back to normal. But sometimes if it doesn't do that, it will actually have to produce more of that hormone. This is why blood sugar sometimes is so hard to regulate. Your pancreas is responsible for producing insulin. But if you have so much sugar coming in, your body goes, all right, here's some insulin. Wait, what's that? That wasn't enough? Really? Okay, great, make more insulin. And then it makes even more, but then all of a sudden, like all the sugar gets pulled out of your blood. Now your blood sugar bottoms out and your body is like, hey, holy crap, I've got no blood sugar. I feel ill, I feel cranky, I'm gonna kill someone. You know, like, it's like, get me a donut, you know? And so then you're like, okay, fine. So then you go eat something that's super high in energy. Usually that's something that's high sugar food. That comes in and your body goes, wow, that's a lot of sugar. And then it goes through the same process. Oh, my internet's crapping out.
Yeah, you know, I lost you for a sec, but you're back.
Oy. All right, so let's get through this real quick. So your hypothalamus is the bottom of your brain. It's right down here, and it's responsible for working with your pituitary gland. You got two different lobes of your pituitary gland, by the way. Like your pituitary has like its anterior lobe and its posterior lobe. They stimulate different types of hormones. But honestly, like I said, again, not that it's not important, but like we're gonna kind of move past it a little bit. So the master gland, it releases hormones that affect other hormones, right? Hormones working with hormones. So you've got the anterior, posterior, and this word that I always have trouble saying, infundibulum. No, that's not right. I doubled it up. Infundibulum. Ah, there we go. That's technically correct. Almost. I attacked the word too hard in the beginning. So your hypothalamus will, so here's how that kind of works, right? Your hypothalamus will release some type of hormone, whether it's a releasing hormone, which triggers hormones, or an inhibiting hormone, which still releases hormones, but it releases anti-hormones. And so that stimulates or suppresses those pituitary secretions. and then those signals will affect your body. So some of that's your growth hormone, some of that's your thyroid stimulating hormone, some of it's that adrenocorticotropic, some of it's like prolactin, right? Prolactin, for instance, is like part of the hormone that actually helps like pregnant mothers produce all the things that they need to do in order to like produce nutrients for their young. There's also follicle stimulating hormone. This is a hormone that you start producing once you hit puberty, and that's how some people start to grow like body hair. You know, I was joking around like, I've got like, this is so personal, but I've got so much freaking chest hair. Like, just like I wish that I could kill my follicle stimulating hormone, but it would mean like even less hair on top of my head. But that's like, man, like I always joke around and say that like if Robin Williams got together with Sasquatch, they would have me. There's also luteinizing hormone, which is a really big one. That's what helps you have like healthy hair, skin, and nails. Lots of these different things. You've got antidiuretic hormone, which pulls fluids into or out of your tissues. Oxytocin, which is my favorite of hormones. This is actually nicknamed the cuddle hormone because your body produces it when you give people hugs and when you feel like affection. Again, pregnant mothers will actually produce high levels of oxytocin, which is what helps in like the bonding. And this is oftentimes why like, you know, aside from like any like emotions or anything like that, this is often why like certain, you know, mothers will bond to their young much harder than like males will in the beginning, because like they'll be saturated with oxytocin. A weird example of this is if you ever see like animals, let's go ahead and talk about like cats again here real quick. But do you ever see like those videos where like a cat will adopt like a duck, or like it'll adopt like a pet rat or something? Like you'll hear, or like a cat or like a puppy, and it's like cats and dogs are enemies. No, like you'll have like a mother dog will, you know, lose its babies, and then all of a sudden there'll be kittens. They'll put them in there, and like those kittens will like, you know, that is because like of high levels of oxytocin. That animal is more likely to respond and be motherly. I watch I love videos like that. I watch them constantly. That's like my favorite like type of video, is like where it's like, this cat adopted these ducks, and I'm like, oh yes. Or like this baby
I know, it's
squirrel.
so cool.
Oh, I love stuff like that. And that can be explained through like cuddle hormones. So here's all the different types of hormones. And like I said, I'm not really going to go through each and every one of these, but you've got thyroid stimulating hormone, adrenocorticotropic hormone, you've got testosterone, estrogen, progesterone. Those are our sex hormones that give us like specific sex traits, you know. One of the reasons men have more type 2 muscle fibers is because testosterone is an anabolic hormone that produces muscular growth, whereas women produce estrogen more commonly. Men make a lot of testosterone and a little bit of estrogen. Women make a lot of estrogen and a little bit of testosterone. And that's what gives us our specific sex traits. And this is, again, like, this is where, like, you know, hormones really do control, like, what your sex is. And that's sort of where you will see, like, different traits exhibited in, like, different people in very, very different ways. It depends on, like, what your levels are. Your thyroid is right here. This is one of the biggest ones. This kind of controls like how fast your metabolism burns. And so you'll actually notice it's right here on the back of the neck. And sometimes you'll see people who have like thyroid disorders, right? Where this is either shut down and they'll just
I have that.
like just feeling, yeah, you get a slow thyroid?
I still do a hypo. I have hypo. It's slower, but I told my endocrinologist, I'm, you know, it's usually for life. And I'm like, no, screw that. I'm not going to be taking, you know, I'm determined to get off the pills. So I think exercising is going to be very helpful with that. And, you know, because if you could do it with like diabetes and cholesterol, you know, through changing your lifestyle,
oh, absolutely.
I believe it. Yeah, it can work for this as well. Because usually this is like for life, usually, you know, with the,
sure.
Yeah, but
it's gonna sound
not
kind of crazy, but do you ever eat any like shellfish, like clams?
I do, clams, scallops, and all that.
Yeah, those are really good for hypothyroidism actually, because they're high in iodine, and your thyroid uses iodine actually as like it promotes like thyroid health. So that's one of the like important ones to have in your diet. I mean, everybody needs iodine, but like, you know, in a
And
weird
seaweed and stuff.
iodized salt might help you, but it's better to just get it from, get it from like a healthy
Straight
source.
Yeah, right.
So you got thyroid hormones like thyroxine. I'm not even gonna try and say this one. Triiodothyronine. T3, that's what everybody calls it. Calcitronin, this is kind of fun. Your thyroid actually does help your calcium metabolism. So sometimes like when you have like hypothyroidism, you might find that you don't synthesize vitamin D or calcium quite as well. So another part of getting your thyroid going is getting plenty of sun in your diet so that you absorb vitamin D. And then you've got your adrenal glands. Kind of weird. You would think your adrenal glands would be, maybe somewhere in the brain where you're like amping up, but they're actually located on your kidneys. It's like your kidneys have these little hats on. Those are your adrenal glands, which is also why sometimes you'll have like, you'll get ill. You'll get this like gut feeling sometimes when you start producing too much adrenaline. Epinephrine, which is your fight or flight hormone, that is definitely one part of like your adrenal glands, right? When I say adrenaline, I'm actually talking about its first form, which is epinephrine. This is what we say when we say like adrenaline. This is its real form. But sometimes it also produces things like cortisol. Cortisol is a stress hormone as well. Cortisol gets a bad rap because it does all these things that we don't want it to do. Cortisol, for instance, is like a fat building hormone. Cortisol is a fight or flight hormone that like when you are in a stressful, dangerous situation, you'll produce a bunch of cortisol, which will send your body into like, storage mode. It's like, oh my God, start making some fat. Apparently we're on a deserted island and we're screwed, right? So we often want to avoid cortisol, but we need cortisol because it's what gives us stress to like, positively live our lives. I always tell people you would never pay your bills if you didn't produce cortisol. You've also got other things like your aldosterone, and you've also got your sex hormones, testosterone and estrogen, like I mentioned. Your pancreas is producing certain enzymes, but part of its biggest thing is to produce insulin and glucagon, right? Insulin's job is to lower your blood sugar levels by pulling sugar out of your blood and sending it into your cells or converting it into glycogen or converting it into fat. And glucagon is going to increase your blood sugar by saying, okay, well, this is great. I have all this glycogen stored, make some glucagon, boom, and that's going to trigger the release of that glycogen into your bloodstream to get your blood sugar levels back to normal. But if you produce glucagon, your body is also going to produce hunger hormones as well, like in the form of ghrelin. And that's going to make you super, super hungry. And now all of a sudden, like you need to eat and your blood sugar levels spike. So it's rare that we are supposed to produce glucagon. It's a good thing. It unfortunately comes with the negative side effect of often causing us to bring in a ton of calories. So there's the pancreas there. So actually, this is actually describing exactly what I just mentioned. So let's say your blood insulin level goes up, right? That's going to drive your blood glucose levels down. Then your body goes, okay, our blood sugar is too low, so then it produces glucagon, which is going to raise your blood sugar levels, but now your blood sugar levels are too high, so your body's going to produce insulin, and it's a circle. So that can sometimes lead to things like, and there are a ton of endocrine disorders out there, but the most common that we end up seeing is diabetes, right? Type 1 diabetes is where your body's pancreas doesn't produce enough estrogen, enough insulin. And then type 2 diabetes is a not rare disorder, but it should be a rare disorder, where your body cells have actually become resistant to the insulin. And so now it's not working anymore. It doesn't pull it out of your blood. So your body goes, oh my God, why isn't this working? More and more, and it makes more and more and more and more and more insulin. So your pancreas works fine, but your cells have become resistant to it because they're experiencing too much insulin all the time, and they've become desensitized. You've also got your sex glands, which are going to produce testosterone, estrogen, and progesterone. So The testes produce testosterone, the ovaries produce estrogens and progesterone. Both those things are really important for regulating normal function within the body. For instance, estrogen is really important for helping women uptake calcium. Testosterone is really important for men to do that. So we definitely need both of these things. Make no mistake, like a lot of guys are trying to avoid estrogen like the plague, and that's fine because too much estrogen obviously can lead to sort of these like physiologic changes. But we want to make sure that like we still have it. It's an important hormone. Same thing with women, right? Women often want to avoid making testosterone, but again, it is important to all of us. We want to have a balance though. And then we've got talking about like cascades here real quick. If you are in too much of a fight or flight response, your body will create a really intense response, and then that'll like trigger all these things. And if you can't get back into balance, that's a cascade. And if it really can't get into balance, that can even lead to a thyroid storm, which is honestly one of the most dangerous things. A lot of I mean, this sounds terrible. I'm not saying a thyroid storm is totally incurable, but a lot of times when somebody experiences that, it's like the doctors really can't even get them like under control, and sometimes people will just overheat and die. There's a really sad story out of Australia a few years back of this woman who was taking different steroids, and she started experiencing like a thyroid storm, and her parents like called her and they couldn't get a hold of her. They went to her house and they found her sitting in the bathtub, and she was just overheating. She had like sitting in a bathtub with like ice and water. And so they took her to the hospital, and the doctors were like, there's nothing we can do. Like, you know, you should get your affairs in order because you're going to overheat in the next couple hours. And it was really sad.
But didn't she take? Yeah,
that?
Go ahead.
Yeah, that's why we don't want to take steroids.
Steroids. That's what. Oh, so that was the okay.
Because you're just injecting hormones, you know.
Mm.
So stay away from stay away from steroids. All right, that's about all I got for you. Do you have any questions?
I have a question about the book, Brad. Maybe it doesn't need to be recorded, I think.
Oh, no problem. All right, so we'll end today's recording. I'll see all y'all tomorrow.